the nice introduction, especially for inviting me. This is exciting. So I kept this very, I didn't know what to expect. So I kept this very informal. I have a few slides here and there that I very often present, but I very much enjoy the fact that people engage with me, ask questions, interrupt me. Basically, what I want to talk about is just things that interest me, and then we'll see where the discussion goes. This is not, I don't intend it as a sort of like academic presentation the way probably you are used to. I can, if you want, just be that, but I would prefer not to. All right, so the very title of this presentation is a question, and that's why I want the presentation to be a bit more interactive. So I do have slides, but if you want, I mean, especially because you're so far into this course, it would be nice to hear your perspective as well. So what do we need to simulate and program robot swarms? That's the fundamental question. Now, how much do I need to introduce swarm robotics? Can I skip a little bit, or you want me to be a bit structured?
We appreciate an introduction, a new language, or your perspective on swarm robotic, but we already had some overviews, so feel free to speed it up, but definitely I would love to hear your words.
So let me just use this then. This was an introduction to swarm robotics. That's the, oops, this video is here, sorry. I'll get it quickly. I usually start with a couple of videos that, or at least one video that I find particularly interesting, which is this one right here. Let me share my screen here. All right. Okay. So video number one would be this one right here. Here. All right. This video right here. These are ants carrying leaves. You might have seen this video before. Have you seen it? Yes. Okay. So this was an National Geographic video. One of the things that fascinates me about collective systems is just how complex is what they do. Now, these are ants that are in a world that is incredibly dangerous, noisy. They have no map. They have very limited cognition, yet they are able to, perform tasks of this kind. So one of the things that fascinates me is exactly how to achieve that. And one of the things that early on in my career I discovered, though, is that to study that, you need good tools. And so, yes, in order to get there, even during my PhD, I first had to take a step back and say, wait a second, it's not so easy to study this stuff. And this basically made me into a person that works partly, and I have a lot of work I'm not going to talk about today, on algorithms and human swarm interaction and stuff like that, and tools. Tools is just like, what do we need? It's really just a fundamental question. So the interesting thing about swarm intelligence that motivates us to be probably in this class together is the fact that we take inspiration from nature because we know that nature has done it, and has done it in a way that is efficient, robust, parallel, and adaptive. And I don't want to go too much into details with this, but we can if you want. What is important about swarm intelligence is to understand that it is a science in its own respect that tries to basically reproduce what we see in nature. What is interesting, and in my opinion, what is motivating, is the fact that we're not trying to build something that doesn't exist. We're trying to build something that does exist, but it's so incredibly alien to us. And there's a number of design principles that then will play an important role in the tools that we make. One is the fact that we want to talk always about decentralized control when we want to take inspiration from social insects. The second one is that we want simple and local interactions, and that affects our tools because it's all about communication. And typically the volumes of communication are not so simple to characterize. Have you talked about stigmergy, for example, in your course? Yes. Yeah. All right. So one of the things that is interesting about communication is the fact that Sometimes you want to talk very often, sometimes you do not. Sometimes you want to talk directly to people, sometimes you do not. For example, stigmergy is a way to just leave a mark, and whoever gets the mark, it's okay, but I don't care who does. So it's a way to modify the environment, but I don't care who gets this modification, for better or worse, by the way. But the point is, the communication modality that we have in this kind is not a communication modality that, for example, is Wi-Fi. Wi-Fi is a different one. It is one-to-one communication. When we make tools that need to be able to simulate communication, we need to enable all of these things, for example. And when we program robots, we would like to be able to take advantage of all of these things. Then obviously we want the robots to be cooperative. We want some sort of redundancy. And I'm sure that Heiko talked a lot about, the role of redundancy and scalability and the fact that, we want a few extra robots, but when we have too many, we spend all of our time avoiding collisions and, diminishing interference. So that, redundancy in itself is an extremely interesting topic of research in swarm robotics. And then we want to do task allocation, so there's no predefined roles. There's a lot of interesting applications, optimization, networking, data clustering. We don't care about any of them. It's really just about robotics today. So we can see that swarm robotics is at the intersection between collective robotics and swarm intelligence. Swarm intelligence intended as a discipline that studies how to make systems that are inspired by insects, not necessarily robotics. Collective robotics is how to coordinate many robots, but not necessarily the way insects do. And then swarm robotics is really a combination of the two. There's a lot of applications. Let me go fast on this because otherwise it's too boring and I would like to get to the point. But you have exploration, construction, search and rescue, monitoring, mining, demining, nanotechnologies. These are just some of the applications that you could possibly think about, and there's so many more. At the time of making these slides, I completely forgot that there's all of the underwater applications, for example, that are so exciting. And so anyway, so what's interesting? What's interesting is that all of these applications have in common the fact that the environment is typically large with respect to the size of the robot. Think about the size of a planet, think about the size of the ocean floor. The idea is that we have tiny, tiny robots. It doesn't matter how big they are. They can be as big as a bus, but still, the environment is so much larger than what they can occupy. The second thing is that we are involved with diverse physical phenomena. This means a lot of things. It means that we have robots that are on the ground, and so we have terrain interaction, and then we might have drones, so we have wind, and then we have communication issues. So we might have to consider things like if we're in a cave, the fact that signals bounce in funny ways. We have to consider communication interference, congestion. There's so many diverse physical phenomena. Swarms fundamentally need to be heterogeneous. I'm sure that this is a point that you covered a lot, but a big chunk of my research, my recent research, by the way, is about being able to coordinate robots with different skills. I'm not going to talk about it today, but I'm saying this is one of the most recent things I've been working on. It's really unavoidable that the swarms will be heterogeneous. And in general, everything is very complex to analyze, to think about. That's why we do research on these things, because they are exciting, but also because they are hard. So in my past, I had some work done really as a student when I started in the SwarmBots project that focused on task-driven self-assembly. So robots that could connect to each other and do things as a connected unit. For example, push a ball that a single robot wouldn't be able to do that, but when you connect together, you can push the ball. So the robots need to be able not only to move and so on, but they also need to be able to form new structures. So if you want to make simulators that do these things, these are a lot of different requirements already when you think about being able to support all of these things. And then if you want to change shape, you need to be able to do this, but mind the gap. You need to be able to be in 3D in this case, because the robots need to be able to to fall in case things don't work. In other cases, we had this bridge that was slippery, and we wanted the robots to connect to each other, so the robots would not fall because they could go through the bridge, but alone the robots would slip because this is a cylinder. So we evolved this concept into the Swarmanoid project, which is this combination of 3 different robots. So we had a number of things that we wanted to do with these robots. We had I have a few videos here, but I'm not sure if it's. Let me just skip the video. I'll show the video at the end. I just want to get to the point. Anyway, so Swarmanoid was a project that combined robots with different features. So we had ground robots, we had robots that could climb. So we had different types of robots that also had different capabilities. When we talk about applications, we talk about shape formation with robots. Again, I want to go a little fast here. If you won't stop me anytime, as I said. But anyway, this is a nice video in which robots form the EPFL logo that I always find very fascinating, because the robots, are not using. Well, let me stop there for a second. I actually want to see what people say about this one. I'm really curious. Let me show you this video. I will get the video because I actually am curious about this. Just here, it's here. All right. How do you think we would make a video like this? I'm actually curious. And then because this actually matters for programming later on. So I'm actually curious to know. So we have this video of 278 epochs that are forming the epoch logo. You know the end because you saw the picture, and the robots look like that. And then in just a matter of a few seconds, they would form the logo. How would you do that? I would like to hear from you, because this is a class, and I'm just curious to see how you guys think. Anybody, please.
So with kilowatts, we have a trick, and we usually reverse it.
So this is the way this was done, okay, which is very disappointing, but at the same time, it is advertisement, so why not, right? So that's fine. But if we wanted to do something like this for real, it would be very, very hard for a number of reasons. The first reason is that the placement of the robots is perfect, absolutely perfect. And the second thing is that the robots are avoiding each other really well, despite having to form these very tight structures that are really hard to form. We're basically fighting against entropy here. So what I wanted to get to essentially is that even in forming something like this, when we think about a system of this kind, it is not just Python and it is not just ROS. There's a lot of extra mental models that we need to build. All right, so this is again to build some intuition about, or at least my way of looking at swarms. So in general, what we know is the requirements that we have at the high level, but we have to consider that the implementation is unknown. And we have to consider space-time factors like coordination, communication, and deadlines. We have to consider physical interactions like collision and interference. We have to consider scale factors like the fact that we have lots of robots and environments that are very large. And so typically people design systems in two ways, either automatically, and especially lately there's a lot of machine learning that is going into this, but the old school method was to do evolutionary methods. And then we have manual methods, and manual methods are more the ones I'm talking about today. It's about programming and basically designing. Let me skip a few slides on this so I don't go too much into things that people might have already talked about, so I don't want to stay there too much. Let me just get to this. One important thing is that when we get to finally have these systems, we want to get these systems and test our ideas. And the way we do it is through modeling, and that's finally where we get to simulation. There's, in general, three ways of modeling systems. What we call macroscopic models, for example, thermodynamic models, or in decision-making in particular, there's a lot of interesting work done by Giovanni Reina, for example, that you might know, in which they use flow equations to model the processes of decision-making. These methods are really good, but they have a fundamental defect, which is they abstract away completely for example, the network nature of the robots. They just consider them as a group. But still, you can get a lot of interesting insight. Then you have microscopic models. Microscopic models are the typical things you do, for example, with Gazebo or with Argos. So you take the individual robots, okay, and you simulate them one by one as accurately as you possibly can. And so typically you have mechanical models, you have models of communication. And then you have what we call mesoscopic models that usually you probably haven't seen, but they are models that take the perspective of a robot and then treat everything else as particularly disturbance to that robot. And I have used a little bit this concept myself in some work recently. Typically, the equations that you use on some modification of the Fokker-Planck equations, if you don't know what I'm talking about, it doesn't matter. But it's just to give you an idea. There's lots of different ways to model robots. So if we want to model robots, what do we need? Well, we want to be able to have experiments in which we have flying robots and robots that can connect to each other, we said. So let me skip these videos so I can get a little bit more to the ideas. We would like to be able, by the way, our simulator to be ugly, so to be in our jammies when when we are just doing prototyping. But then when we make videos, we would like to have high quality videos, and I have a high quality video here. Again, I would like to skip a little so I can get to the interesting part. And then we would like to be able to simulate robots with different capabilities that can potentially connect to each other. So what would we like to have? Fundamentally, we want three things: accuracy, flexibility, and efficiency. These are the three big things that we want. Why do we want accuracy? Well, because otherwise, what's the point of even simulating? Why do we want flexibility? Because we have so many different requirements about the type of the robots and the type of applications that we have in mind. And then obviously, we want to do it efficiently. Now, the question I have for you is, why do we want to do it efficiently in particular? I have another slide later that talks about this slide, but why do we need efficiency? And if you want, do you see other requirements as well that I'm not considering? Does anybody want to try? Okay. Well, one of the reasons for efficiency is that we have lots of robots. And so if you have lots of robots, simulating lots of robots is very hard. But this connects to the problem of the reality gap in particular. And I would like to get to the reality gap. The classical reality gap that you might know is that there's noise in sensors and actuations, there's real-world physics to consider, there's hardware calibration, there's latencies and delays in processing and communication. That is the boring classical sim2real gap. It's not so interesting, meaning that it is obviously interesting, it's obviously very hard, and there's people dedicating entire PhDs to it. But swarms are special. Swarms are special because there's extra challenges that nobody else has. In particular, we have the fact that we have emergent behaviors. An emergent behavior, by definition, okay, by design, is a behavior for which we couldn't anticipate all of the effects. And so we discover very often that simple mechanisms can create very complex mechanisms, but as much as a nice behavior can be emergent, there's a lot of bad things also that can be emergent. One of them, for example, could be congestion. And it's something that you need to test for because you can't predict it. So emergent behavior can also be emergent bugs or emergent difficulties. The second thing is that some effects that we have are scale dependent. So if you have a small simulation with like 3 or 4 robots, there might be no interference in radio, and there may be no disturbance in airflow in drones. But when you have a lot of robots, this becomes much more apparent. Then you have the fact that no two robots are ever built in the same way. So when you have a lot of robots, you start seeing that certain robots are faster than others, even though they are supposed to be exactly identical. There's one interesting example from the 2 robots, Spirit and Opportunity, that were sent to Mars. They were absolutely identical when they were sent to Mars, but they were sent to different environments within Mars. So in one case, Spirit was sent in a certain valley, and Opportunity was sent in a place that was a bit more less flat, and it had more basically let's say the terrain was a bit more rocky. Anyway, in the space of 6 months, the 2 robots became different, to the point that the team that could control one robot didn't know how to control the other one, because the robots basically broke in different ways. Okay, imagine not having just 2 robots, but having hundreds and then sending them to the moon. They're all going to break in different ways. And then the idea is that if you combine all of these things, the number of testing conditions that you need to convincingly consider grows exponentially. You need to try so many different things. So efficiency becomes important because of exactly that reason. Okay. So when you look at the current state of the art of simulation, you see that there's certain simulation, like for example, Gazebo is probably the one you know, WebBots, UserSim, and VREP. that mostly work on this axis. They are somewhere between the accuracy and flexibility axis. They say we can, for example, simulate any robot and any condition, and we can do it somewhat accurately. I have my own difficulties with Gazebo because it's not so accurate, but that's okay. We can talk about it if you want, but it's not so important. But the thing is that they sacrifice efficiency. You cannot, if you try with Gazebo to run a simulation with 100 robots on a laptop, you simply cannot. It's just not feasible. Then you have another axis, which is not very studied, which is the axis of flexibility and efficiency. The idea basically is to have little simulators that are specific to certain use cases. One of them is Breve, and it's a really nice simulator. But it's not very accurate. In that case, your little agents are like little animals that do nothing special. They're just little circles that can sniff the environment and do very little things. And then you have simulators that are incredibly efficient, somewhat accurate, but they have no claim on flexibility. I mentioned Stage because it's famous, but there's also Quilombo for those that do kilobots. There's Enki for those that play with epochs. These are all simulators that are custom made, and very often just people make their own. The question is, can we conquer all three at the same time? And that was the job of Argos, which was, by the way, one of the outcomes of my PhD. I followed 5 principles in doing that. And by following those 5 principles, I also discovered that nobody cares in swarm robotics. I mean, people care about the product, so they cared a lot about the simulator, but they didn't care about how it was made. But unfortunately, this class is partly about that. So for the next 5 minutes, you have to care. So I have these 5 principles in mind, which is interesting because these are 5 principles of software engineering. So let me just talk for a second about software engineering by talking about large language models. I know that today, and I use, by the way, large language models. Today, large language models are very exciting. But let me make a very controversial claim about large language models and the current state of machine learning. Let me claim that it would be literally impossible to have this kind of intellectual push that we have today in these fields if we didn't have first literally 20 years of hardware, software, and data science. This is a very important point. Nobody cares about software engineering in robotics, also because the field is dominated by mechanical engineers, or anyway, people that understand mathematics very well. And so they see programming as sort of like, this is the boring thing that they do in companies. The reality is that we need new concepts, we need new ideas, we need new tools, but not just old stuff that just does new things, but we need new ideas, new concepts. And so this is one of the things that in swarm robotics is not sung very much. You would not get many people talking about these things. LLMs in particular, right now, one of the things that made, for example, the new ChatGPT, the O3 model, is not an intellectual leap. It's not. There's nothing special about these models after LLMs were invented. The real thing that was done was conquering scale. And the way they conquered scale was with a lot of very, very, very smart software engineering, which I will not go into, but I'm saying the unsung hero of all this is software engineering and obviously data science. Nobody cares in our field, but I think we should. Anyway, so 5 design principles that I considered. The first one is boring and I won't say much. It is called modularity. The idea is that Argos is a combination of many modules. It is a combination of many modules in a way that no other simulator is, though. And this is interesting. So we have the idea of a space in which a thing called entities goes, which is basically the way a robot is composed. It's just composed of entity. For example, a robot can have wheels. A robot can have, for example, a position. And the interesting part is that the entities are not necessarily physical characteristics of a robot. These are just things that a robot can have, and they are combined into a robot. And then the idea is that each entity has another part of the simulator that deals with it, that can write into it or read from it. This is a different design, for example, from any other simulator you will ever see, specifically Gazebo. Gazebo, for example, a simulator you might know, is a wrapper around a physics engine. Nothing more than that. So they first take the physics engine and then they add to the physical objects extra information. But the point is there is a physics engine at the center. Argos doesn't care about physics engines. I tell you more, our physics engines can be reality. because I can use the motion capture system, and the only thing I need to know is how the robot's moved, and I can plug the motion capture system, and I can have the motion capture system be my physics engine. So that's nice because this basically allows us to be extremely efficient and also extremely flexible. The idea of modularity also comes into visualizations. We can easily switch from this ugly visualization, which is the one that probably most people use, to the nice visualization in 3D that is based on POV-Ray. The second thing that we do is making things composable. Making things composable means basically that because entities can be, the entities, let me show a picture, for example. Because entities store the state of a robot in an abstract way, you can simulate that aspect of a robot the way you like. So for example, say that you have a camera-equipped entity. That means your robot has a camera, but that doesn't mean that is a specific implementation of a camera. That simply means that the camera contains an image, and the image can be generated the way you want. So the idea in this case is that we can take the modularity concept and create as many sensors as you want that generate that image in a certain way. It could be done with OpenGL. It could be done from photorealistic images from a video. It could be done by literally generating the output of a filter. So basically asking, generating the output of YOLO, you only look once. The point is, you don't care about how that is calculated. What you care about is that eventually the camera-equipped entity gets an output that can be given to the sensor to handle. And the same is for all the other sensors that we have here. So what's interesting here, basically, is that you can plug what you want in terms of how to calculate the results and then store them inside the entities. From a software perspective, this is called a DTO, a data transfer object. I don't know if you ever heard of this term, but basically that's what it is. So this makes everything extremely flexible because you can reuse the code very much, and it makes things extremely efficient because it is easy to know where the data is, and from a cache point of view, if you care about cache efficiency, it is very easy to basically load all of the information about all of the robots, put them in cache, and then for loop over them very fast. This is something that Gazebo doesn't do, and basically no simulator that exists today does. All of these things, again, are very much into the software engineering weeds of it, and then they have consequences on enabling swarm robotics experiments. Another feature that Argos has and nobody else has is having multiple physics engines. So the idea is not just that I can plug the physics engine I want. There's one extra step. I can run multiple physics engines at the same time. So in an environment like this that is in 3D, I could, for example, have one physics engine for the floor and one physics engine for the sky. And so I could have ground robots simulated by one physics engine here and then flying robots at the top. Or if I want, I could divide the environment in a room here handled by a 3D physics engine, a corridor in which only the robots that are on the ground can go. So I can simulate just a 2D physics engine, and then I have a 3D engine here. And by the way, any of these engines can be reality, because if I have, for example, a room right here that is handled by a motion capture system, I can make hybrid experiments in which I have some robots that are physical and actually do things in the world, and they talk to robots that don't exist in the next room, and the next room simply is not there. It's just not a room that exists. So what's nice about this is that we can do human swarm interaction very easily. We can add virtual robots, we can add virtual environments, and we can simulate things that are not there. So we can use any kind of physics engine library that you want. So there's a bunch of them that are all very similar. Right now, all the rage is having differential physics engines, to do soft contacts and stuff like that. You can do that in Argos if you want. And then it's very efficient. It is efficient because, first of all, imagine that I have, 1,000 robots. Well, I am dividing 1,000 robots into different physics engines. And so it matters, even if the complexity of calculations is square, which is usually not. It's usually in the order of log n, or log the number of robots. Sorry, n log n. But I'm saying, even if you have a stupid physics engine that is n square, the interesting part there is that you are lowering the number of robots handled by a physics engine. So you're making them more efficient. And then the code can be optimized for a specific use. Okay. The reality gap is handled specifically by another thing, which is called tunable accuracy. So tunable accuracy is this idea that you can decide which model you use for which use. And so this affects basically every module. The idea here is that if you want a sensor that is specific to a certain use, you're going to use that. And maybe it's not very expensive because you don't care that much about simulating that proximity sensor so well. If you want to have complex terrain, you can do that too. Okay, because that is important to your experiment. The point about tunable accuracy, again, is a concept that you don't find in Gazebo, and it's important in the design of a simulator. Finally, okay, and this is if you want trivial, you want parallel execution. In this case, in Argos, it's multi-threaded because it is more efficient, and the design makes race conditions absent. Some of the things that are interesting about this design is that it's extremely scalable. So let me show you this video. Let me see if it starts. Yep, it's here. Yes, I have it here. I can show you one result of this. Okay. The other one, sorry, the other screen. Okay. Here. Here. This is a simulation that you can do in Argos, and I did at the time on the computer that I had. It was a 12-core computer. There's a bit of funny artifact noise, but this is what you can do with Argos. I challenge you to do it with Gazebo. Okay, so this is it for simulation at the moment. I have more, but I would like to stop here in terms of simulation. I'm happy to chat a little bit about programming, but if you have any questions or, whatever, reactions, I'm very happy to chat about that.
I guess if students or participants do have a question, just feel free to speak up.
Okay, so let me switch to programming. So in this case, programming is, if you want an orthogonal problem to simulation, once you have a simulator that can simulate large-scale systems, the next big thing that you want to do is to be able to program. The typical way in which we do it, I guess, it's going to be with ROS, and it is going to be with Python, because that's usually what people do. The question here again is that what we need, and do we need more than that? So let's understand what a swarm is from the perspective of programmable machine. You can understand a program as a function that takes the swarm state and brings it to a new swarm state. So the question is, what is a swarm state? What are the things that matter in this case? The idea is that the robots connect to the environment. So they have to sense the environment and interact in the environment. The robots have to talk to each other, and then the robots have to have some sort of cognition. So they have to have some internal state that they maintain. So our state needs to include the internal state of the robots. It can be memory or some physical aspect like battery levels. It can be the physical state in terms of mechanics. So for example, the position of the arms of a robot, or whether it has wings and the wings are open or closed or something like that. And then obviously there is communication topology, whether the robots can even talk to each other or not. The environment itself is also important, not just because there's obstacles. That's not so important. I mean, it is important, but it's not the point here. What is important is that the environment can be used as a communication mean, so stigmergy. So all of these things together make you also notice that programming a swarm is not like programming a laptop, and it's not like programming a cloud computer. And the reason is that you can only control part of that state. You cannot control a lot of the environment. Imagine that there's people in the environment. You can't control them. You have to deal with that. And you don't know necessarily all of the relevant important information that are in the environment. The swarm state is also dynamic because the robots keep moving and changing their mind and having new things to do. And communication issues are extremely likely. Okay, so you cannot assume the communication is perfect. If, for example, you would do in a cloud system, let's say. So, and finally, obviously, individual failures are very, very likely. And some of them are predictable, like, for example, battery depletion that you can plan for. Some are unpredictable, so robots just break down because they break down. And the more robots you have, the more robots break down. Even this, just this picture alone shows you that we don't have the tools to handle this stuff today. We just don't. We simply don't. ROS2, these are not an answer to any of this. None of this. They are not designed, by the way, to do this. I know that there's a lot done in ROS2 for multi-robot systems, but when I talked to the people that designed ROS2, they told me that they didn't think about multi-robot systems as a use case. They talked about basically taking ROS and moving it to be more robust, but in the use case of ROS, which is humanoid robots. So I know that people use ROS2 today and they call it a multi-robot framework, but it fundamentally isn't by design. So why isn't it? I mean, what's the point here? So a robot swarm is not a classical distributed system, okay, like a cloud computing system, for example. It is not. And the reason why it's not is that the topology of a classical distributed system is static. Once you connect the computers together, you actually control the topology, and that topology is not meant to change. The communication is reliable and is high bandwidth. Forget that in swarms. And failures are rare. And when they happen, you can plan for it. You can diagnose them. It is not easy to, create a cloud system like the Amazon one, for example, but it is feasible today to do that, as opposed to robotics, which is very, very hard. And that's because these systems are essentially closed machines. There's a lot that you control, and the environment is not so scary outside. Then robot swarms are not necessarily a mobile sensor network. I don't know if you talked about sensor networks in your course. Sensor networks are basically the idea of sprinkling sensors that can be even drones, or they can be physical sensors that are just attached to a place and they don't move. And then these sensors collect information in a distributed way and typically give it to a data sink that collects all this information and does something useful. They tell you the average temperature, they tell you the weather forecast, or something else. The point is, yes, this is similar to swarms, but it's not exactly. The reason is that swarms do not just do data collection and aggregation. It's one of the applications, but it's not the defining application, just collecting data. I mean, robot swarms build stuff, or at least we want them to. Robot swarms modify the environment. Collecting data and aggregating it is one of the applications. Monitoring, sure, yeah, fair. Coverage, yeah, fair, but it's not so important. These are not the applications that we really think about when we think about robot swarms. When we think about robots, I mean, why do I want a robot in my house? Mostly to clean. Oh my God, I would like really a robot that cleans, or a swarm. So sensor networks basically have no actuation unless you talk about mobile sensor networks. In that case, there is motion. But okay, again, there's no environment modification, it's just motion. So it's a machine that is a jar meaning partially open. It is partially open because, yes, we need to deal with the environment, which has unknown dynamics. Think about, for example, a swarm of drones monitoring a fire, okay? But at the same time, we kind of understand everything that is relevant. The only thing that we don't know is the distribution of the data that we receive, but pretty much we control the rest. So what do we want in a language and in a framework for swarms? We want, again, composability, so be able basically to divide our program in functions and classes and stuff like that, the typical things. We want predictability. Predictability is so hard. We want to say basically that if one robot says A is equal to 5, and that robot is meant to tell everybody that A is equal to 5, then in a reasonable time, as fast as possible, everybody agrees that A is equal to 5. And then we would like that if we run the same program twice, the same program runs in the same way. Good luck with that. By the way, predictability is not true with ROS. Do you know why? Does anybody know why? ROS is not predictable. Do you know why? We use tools that we don't understand. All right, so ROS at its base, okay, it's a multi-process system, which means that you don't control the ordering and the scheduling of the processes, because that's done by Linux. If you run twice the same ROS code base and you find a bug in one run, if you rerun the same gazebo simulation, you might not find that bug ever again for the rest of your life. And that is because the bug was due to some funny scheduling ordering that you will never see, because it is not deterministic. So it is not necessarily true that these programs are predictable. And then you want, obviously, support for heterogeneous swarms. So can we do it in ROS? I hope I convinced you that we can't. There's a number of reasons, fundamentally technological why, but also one of the reasons is you have to basically handle every robot individually. Okay, it's good to do that because you have full control, but it's bad because you have an overwhelming amount of detail. There's this idea of spatial computing, which is very interesting, but let me skip over it. It's very, very cool. Anyway, in brief, it's the idea of imagining that the robots are a continuous manifold, and then you program the continuous manifold. You say there is a 5 at this position, there is a 7 at that position, and 5 and 7 calculate the average in the middle between the two. Stuff like that. It's a very interesting concept. It's not used very much in swarms because basically there's no robot, and so you don't know what to do with it. But it's an interesting concept. A friend of mine, Luca Mottola, made this interesting concept that is called task-oriented programming. So basically, you assume that a task allocation algorithm is available to you, and then you only program the tasks, and you assume that the robots can figure out who does what, which is a big assumption, though. So it's nice, but it only works when you can do task allocation very efficiently, and task allocation is a problem. It's a very, very difficult problem. And then you have what is called goal-oriented programming, which is, for example, what you would use to program construction and shape formation, which is the idea of saying, I want this shape. I want the robots to form a line. I want the robots to form a circle. Figure out how. You know, I program the shape, but I want you to figure it out. And now this is typically done in drone shows. You define the shapes, you define the schedule of the shapes, and then you press a button, and there's a scheduler that does that for you, that basically programs the trajectories of the robots automatically. There's a lot of research on this, and it's very interesting. So why did I invent Buzz? Because I wanted to generalize over all of these things. So I had paradigms that are robot-oriented, so basically like Python. I have swarm-oriented primitives, and I'm going to briefly go through them, just a couple of minutes. I have neighbor management primitives, and then I have global consensus primitives. It's a programming language, basically, that gives you some features that other programming languages don't give you, okay? And what is nice is that you can put it on any robot. It looks like JavaScript or Python, so you can program fast with this. You learn in a day, usually. And you can put it on any robot you want, because the VM is written in C. So the idea is the robots are at the same time seen individually and in a step. So you have a little step function like in Arduino, if you want, that you need to implement. And then each step goes into phases. And we assume that the robots have situated communication. This is something that can be implemented in reality. So we have a robot, we have a communication range, and then some neighbors are within the communication range and some neighbors are not. The ones that are send you a message or you send them a message. And so, for example, if this robot sends a message, it's going to send a message to this robot, and this robot knows both the vector to the robot that talked and the content and the angle, obviously, and the content of the message. This is called situated communication. If you do this, you can do flocking, you can do foraging, you can do basically everything. So we have a data structure and a primitive called neighbors that allows us to do both managing positional data and communication. So for example, we can easily program things like a gradient. So we can say broadcast on a certain topic, a certain value. And this little code right here says, I want to listen on the topic distance. And then when I get a value on the topic distance, I'm going to consider the topic, which is distance, the value, and the neighbor ID. And what I'm going to do is an operation of min between the value that I already know and the value that my neighbor gave me, which is val, and the distance to that neighbor. What does this algorithm do? It's a gradient algorithm. It basically says, let's say we have two robots that know their distance to a target location, and we have three robots that do not. But we have the mutual distances because of situated communication. If you run that program, in the end, every robot will have an estimate of its distance to the target location. What is nice about that piece of code is that it is reusable. There's nothing there that is specific to having wheels, having flying robots. It's just a very generic piece of code. And that's one of the things that Buzz is very good at. It's creating swarm libraries of robots that then just need to have some special feature, like I move by flying rather than by moving on the floor. I can do things like reduce, which is aggregate the data over the neighbors. I can modify the data of the neighbors. I can filter my neighbors according to some features. And so, for example, I can calculate the average position of my neighbors, and I can go to that average position. I can transform the data of a robot into something else. And so, for example, I can transform the data in cylindric coordinates into Cartesian coordinates with just this piece of code. And what's nice, again, is that this is part of the library. So it's a little function that you can reuse. And I can filter the robots and say, I only want the robots that are within a certain distance from something. Let me just skip here to the other feature I wanted to talk about, this one, and then I guess I'll stop here. One thing that is really nice is that you can do swarm-oriented development, which is another thing you have never seen before in other programming languages. Imagine that you have a swarm of different robots. You can tag each robot in the way you want, like you tag, for example, emails in Gmail or in Outlook. And so you can, for example, have a tag for the robots that have wheels, a tag for the robots that have a gripper and have wheels, and then you have a tag for the robots that can fly. And if you use this tagging, then you can do things like use the tag to say that a tag is a task. And so you can tag the robots that are working on a task with the tag, task, whatever, move object. You can tag the robots by their physical features, so you can handle heterogeneity. You can tag robots by the team they're part of, and you can tag the robots as a finite state machine. So basically, you can tag the robots by saying we're all in this state. When we're all done, we move to the next state. So you can use tags to do these kind of things, and it's very simple to do. You create a tag like that. You give it an ID that is unique across the robots. Then you select which robots are part of the tag with a single line of code, and then you can execute a function only for the robots that are part of that tag. And I have a lot of code examples that show how this can work. I think I am at the end here, so I don't want to go over my time. These are just some ideas of the things that we might need and work that I have done. Obviously, there's an entire discussion that we could have about all of the things I haven't done and we need, and it's still research I'm doing. But let me stop here for the time being. I hope it wasn't too boring. But these are just some of the ideas of like why software engineering matters in robot swarms, because it enables new ways of thinking and new applications that we otherwise wouldn't be able to.
Thanks. Thank you very much.